Hello, everyone. My name is Narcis Salala, and I'm currently an undergraduate senior here at Texas Tech in the Mechanical Engineering Department. And in this research entitled Electromagnetic Actuation for a Microfluidic Mixer, we are working on actuating fibers at the macro scale. Specifically, I am in charge of creating an electromagnetic device that can be turned off and on at specific frequencies. And in my case, it's 500 hertz. So a little bit about the background and introduction. What is an electromagnet? This is simply just a magnet in which magnetic field is produced by an electrical current. So if we had a piece of copper wire connected to, let's say, a 9-volt battery, even though the strength would be weak, there would still be field lines there. And depending on the resistance of the wire, it might just cause a low current. Before, the old methodology was having a magnetic stir, which had two bar magnets which generate the field needed to actuate the fibers as seen in figure 1. But there are certain limitations to the bar magnets themselves, such as the strength of the magnet, which cannot be increased at all, and the frequency range of the actuation. And that is why we switched to using electromagnet, which we thought would remedy this. Since I've been working on this at home due to limited access to the labs during the ongoing pandemic, what I am and have been trying to do is have, let's say, copper wires that I took from a vacuum and wrapped them around a ferromagnetic material. And in my case, it was circular steel cores seen in figure 5. And I would pass current through them using a type of voltage source with the toggle switch connected so that I may be able to control the electromagnet and the system. So when we turned on that electromagnet, we saw that the system became magnetized because of the field generated. And when turned off, it should demagnetize. When trying to simulate the procedure in Python I was trying to perform, I created a 3-dimensional coil in space, and I passed current through it as seen in figure 3. And in figure 4, which shows the cross-section of the coil in the XZ direction, something really interesting to note here is that the center, you have the greatest field strength as indicated by the yellow line. And the farther away you go from the center, your field strength becomes weaker and weaker. This is also a 2-dimensional representation. In reality, the field would be moving and wouldn't be as static as the figure. So what are the advantages of using an electromagnet rather than a bar magnet? First, an electromagnet, the field itself can be changed by controlling the flow of the current through the coil. And with an electromagnet, you can easily increase the strength of the frequency of the field by increasing the voltage source or even changing the core material that's being used. Another benefit is that, as seen in figure 6, Marcus, my graduate student mentor, was analyzing a specific types of fiber which reacted this way. That's why we see this pattern, but for demonstrating dynamic of the fibers, here would be due to the field itself moving. So when we use an electromagnet, we see a relatively uniform rotational dynamic flow. This, of course, is still a work in progress, and I haven't even began to scratch the surface, so I will continue to read more and learn more. Some upcoming events that will help on my research is with my advisor, Dr. Aksak. By knowing what the gradient is, which is just a perpendicular vector to the magnetic field, I can simulate that and use Python to calculate the gradient of the field. And once I've completed this, I should be able to build a functional solenoid. And the final goal is to simulate a 3-dimensional field. This is the end. Thank you for taking your time to listen to my